We now prove that limit of x raised to n minus a raised to n upon x minus a as x approaches a is equal to n times a raised to n minus 1. Now we know that x raised to n minus a raised to n could be factorized as x minus a into x raised to n minus 1 plus a times x raised to n minus 2 plus a square times x raised to n minus 3 and so on, and the last term would be a raised to n minus 1. So using this identity we could easily prove the required. So our left hand side is limit of x raised to n minus a raised to n divided by x minus a as x approaches a. So we replace the numerator and we obtain limit as x approaches a. Now numerator over here we replace it by this right hand side over here. So we just factorize this. So we have x minus a into x raised to n minus 1 plus a into x raised to n minus 2 plus a square into x raised to n minus 3 and so on up to a raised to n minus 1, the whole thing divided by x minus a. Now we observe that we could easily cancel x minus a with x minus a. We could obviously write the reason here as x approaches a. So x minus a approaches 0 and hence x minus a is not equal to 0. So we are left with limit as x approaches a of x raised to n minus 1 plus a times x raised to n minus 2 plus a square times x raised to n minus 3 up to a raised to n minus 1. And now we could substitute the approaching value of x by a. So simply plug in a over here. So we have a raised to n minus 1 plus a times a raised to n minus 2 plus a square times a raised to n minus 3 and so on. Now this would repeat n number of times, right? And if we observe carefully, it's the same term, right? N times. So it is a raised to n minus 1. Now again, if you use law of indices, see if this power is 1, so n minus 2 plus 1. So that's nothing but a raised to n minus 1. Again, this would be 2 plus n minus 3. If we add the powers, so again it would result in n minus 1. And this would be going on till n times. So basically our answer is nothing but n times a raised to n minus 1, which is equal to the right hand side.